So here you guys will get a rare overview of the design process, the consideration that is done, and I guess the whole process behind designing such a system. The first thing that is done is to make a requirement specification. What do we want to have in our system, and what don't we want to have in our system? What is the most necessary and what is less necessary? These will be all usually documented in this kind of document, and the requirements will be listed as functional and non-functional requirements. And here you can see a portion of these. There is different ways to structure this. I used this SysML way of doing it. The way you can describe functional and non-functional requirements are in the word as shall, must, and should, and may. The use of shall and must means that they are mandatory requirements, that they must be included in the project. Should is an optional one, but it's quite important, so we have to justify that it's not used. And may is one of those things. Well, it could be cool if it was green, but you know, it may also be non-colored. Yeah. So here's the list of requirements. All of this, of course, will be published on the website, which will be disclosed at a later point, I guess. Yeah, that is the requirement, and then some timing plans and blah blah blah. If we look at the structural diagram, I'm still working on this, so these were more meant to be showing you the whole, or just like the design phase of it. When you design a system of any kind, it's very useful to break it down into this hierarchical, whatever it's called, components. So I have made the 3 different levels of this. So the whole airship controller consists of these 4 blocks. A system that will be able to find the positioning in space, the movement control, computation, and power management. And then you can look at the level 2 system, is that the positioning in space is consisted of these 3 blocks: GPS, the initial measurement unit, the wind sensor. The movement control will be controlling the X, Y, and Z components of the airship, and the computation will be figuring out something about what the sensors is telling the system and how it should respond on those measurements, and of course the power management of the system. I won't go super deep into what all these things they do right now, because they probably will be changed quite a lot till the more or less final product. However, I can tell you the main concept of these things. So basically, every single block will be opened up. Basically, this is called the internal block diagram, or this is called a block diagram. That's why block definition diagram, actually. This is internal block diagram. So this shows the guts of all these blocks. And these are the flow ports, so it basically indicates if a signal or some kind of a, it could be like pressure, acceleration, whatever, if it's going in or going out of the system. This way it's very easy to track different things, and especially if there's different people working with different parts. Let's say that one person is building the positioning in space and the other one is building the power management. Well, okay, bad example. Let's say positioning in space and the other one is working on the computation part. So of course it's very important that all the power levels, the communication digital levels, for example, if something runs 5 volt on a microcontroller, you definitely want the positioning in space, the systems, for example the IMU, to be working in the same voltage. Otherwise they won't be able to talk to each other, and you'll probably fry the input ports on this one. So yeah, it's always very important to have a good definition of what the range is, and for example here 5 volts, 3.3 volts, 1.8 volts, and stuff like that. Yeah, so basically we have the GPS system here, the wind sensor, and the IMU. These will be creating the basics of the positioning in space, and they will basically tell us more than we actually need to know. But IMU has so many cool sensors that it's just a waste not to put it on. And it creates an open platform for other people who wants to work on it. Yeah, the power management will, of course, supply power to all these devices. It's important to note that I'm using a buck converter to get a relatively high efficiency on the system, because we don't want to burn all the power on just making a big radiator in there. Yeah, and then small voltage regulators for the small outputs. This will be changed probably a little bit. Yeah, and then we have the movemental control. I couldn't really find a better name for that. So movemental control, that includes the X, Y, and Z directional control. And the way the system works, as I explained earlier, is that the motors will control the X and Y core system of this, the component of this system. There we go. Which will be controlling its movement to right or left and back and forward. Where the Z component will be controlled by another system, where you will blow up a bag of air inside the blimp, and controlling the buoyancy of the blimp itself by this pressure, so thereby not venting any helium or hydrogen. Yeah, so by moving by controlling the motors, which will be done by these ESCs, which is like electronic speed controllers. Look them up; they're really awesome. They will control the three-phase brushless motors that will control the system. And here we have a pump, which is not really decided what kind of pump it's going to be, and a solenoid valve. The solenoid valve will open to let the pressure out, and the pump will pump more air in to raise the pressure again. So it's quite a simple system. And then it has an internal pressure sensor to so we always know what is what in there. Yeah, and then you have the computation. The computation will be consisting of two microcontrollers. One that will, for now at least, because I believe the response time of the movemental one has to be relatively high. Maybe a dual core something will work or some of them, but it's still open. But at this moment, yeah, two microcontrollers. One is controlling all the sensors. That's what you could expect as a captain, basically. It will gain information about the vehicle's position in space and how it's doing and what the course is, and then it will transfer the course to this guy, which you can basically imagine is the sailor on the ship, the guy who controls the ship. And in here there will be sent through SPI a three-dimensional vector that will explain the momentum computer in which direction we are interested to move. And by this it will control all the X, Y, and Z components of the ship and move it to the interested destination. And yeah, and the last thing which I find really neat is that if we get a major power outage on the main battery, or something happens with the battery or it gets flat or whatever, then we can still set the ship down, because the only way we can get the ship down, by the way, like in any way, is by controlling the solenoid valve. That requires quite a little of power, and we can do that on a redundancy battery. So the thought right now is to implement this little controller battery somewhere, which will basically run all the computation on this safe battery. And if something happens, then we'll still be able to see where the system is via the GPS, and then we can find it and we can set it down controllably. Because if we end up powering this thing with the hydrogen, you don't want to have it to drift everywhere with a basically big bomb. And this is the last graph in this case. This is basically taking all those blocks that we have defined up here, the level ones, and now we have the guts inside of them, so we understand what is in, what is out, and now we can combine them or connect them all together, and this gives a really nice mapping of what is going where and how it is going, and blah blah blah. This will of course get more complicated as I make more changes and blah blah, but this is a good way to to have somehow of an idea of what is going on. And when you start building, you can focus on just one little corner and build outwards, and you'll always be sure to, when you connect things together, that things will stay right. So this was my little update, and I'll see you next time.